Alright, third time's the charm. I've tried recording this twice before and I've messed up both times pretty badly, so let's try third time. We're starting off today with electronegativity. This is periodic trend 4 out of 4, so the last one. And I said we'd spend 2 days on ionization energy. I lied to you. That's because I messed up. I didn't think I needed to teach you something until later. Turns out I need to teach you it beforehand. So it's my bad. We're going to get back to that, okay? We're going to get back to it, but we're just finishing off the periodic trends with electronegativity. So electronegativity is a measure of how strongly an atom attracts a bonding pair of electrons in a covalent bond. Here we have a covalent bond between hydrogen and fluorine. This creates a nice acid. And the covalent bond is represented by this rope. The electron on the rope, so there's a pair of electrons here because it's a covalent bond. The electrons are hanging out more closely to fluorine because fluorine is the most electronegative element. So fluorine is saying, your electron will be mine, hydrogen. And hydrogen is saying, no, please, fluorine, don't take my electron. And as a result, hydrogen's slightly positive. This is called delta positive, delta positive, and this is delta negative, which means it's slightly negative and this is slightly positive. If you can write down this definition in your books, because it's quite a common thing to be asked, the definition of electronegativity. So, let's have a look at the data. What does it say? Interesting table. As you can see, a lot of these elements don't have values because they live for fractions of a second, so they can't really be measured. But interesting, we can see that electronegativity increases going up, so starting at 0.7 for francium, going up all the way to 0.98 for lithium, and 2 for hydrogen. And as you can see, it kind of increases going up here as well. It increases going up the table. And it also increases going along the table. So as you see here, it starts with like 0.82 for potassium, and it just increases all the way along. A little bit of deviations. We're not going to worry about the deviations too much, but as you can see, it just increases as it goes along, particularly up here. 2.04 going to 3.04, 3.44, and the strongest element, electronegative element, is fluorine. So why does it increase going up? It increases going up because electronegativity depends on three things. Protons in the nucleus, how many protons there are. It also depends on how many electron shells you have to shield the electrons, because covalent bonding is with the valence shell of electrons, which is the furthest out shell. If the valence shell is far away from the nucleus, it's going to be relatively easy to remove them, or to use them in bonding and to be manipulated. And it also depends on the distance from the nucleus. So down here, francium, there are more protons, but it's so far away from the nucleus, it's a really big atom, and it's got heaps of shielding by the inner shells of electrons, meaning francium has a really low electronegativity. Why it increases going across the table is because we've got more protons in the nucleus. Fluorine has got 9 protons in the nucleus compared to lithium's 3, but they're in the same electron shell, which means there is no extra shielding gained by the extra electrons that fluorine has picked up. So that's why it's so high. No value for neon. You may notice the noble gases, like neon and argon, have no values for electronegativity. Why is this? That's because noble gases, they don't form bonds, and so they can't form a bond to measure the electronegativity in a covalent bond. Because if we go back to our definition, how strongly an atom attracts a bonding pair of electrons in a covalent bond. If you can't form a bond, you can't have electronegativity value. So, But you may have noticed krypton, xenon have a value. How is this? And that's because everything you learned is a lie. Noble gases can form bonds. And xenon bonds, I'm going to put this video in the Google Classroom for you to watch. But yes, xenon can form bonds, and it looks like this. Crazy. This is xenon difluoride, discovered over 50 years ago, so in 1962. And it's a pretty interesting element. So they pretty much only bond with fluorine and chlorine, because these are so electronegative, they can influence the noble gases. So we're going to get to that in just a little bit, but basically same rules as anything. So electronegativity notes. Please write these in your books. Electronegativity is reliant on the number of protons in the nucleus, the distance from the nucleus, and the amount of shielding by inner shells of electrons. So pretty much the same thing as for ionization energy. It's kind of the opposite of ionization energy, if you want to think about it like that. For this reason, electronegativity increases moving up a group. So as we go up the table, it increases because we have less shells, so less shielding by inner shells of electrons and less distance from the nucleus, meaning the electrons are more attracted to the nucleus because they're closer, and so harder to... And so as the electrons are closer, the bond is going to be closer to the nucleus, meaning the electrons in the bond are going to hang closer to the nucleus. And it increases moving across the table. For each added electron, there is an added proton, but there is no added shielding of the electrons as no new shells are added. So if you get out those in your books, and that's where we're going to stop for today. Thanks, guys.